What is going on, guys? I hope everyone is having a great Wednesday. Of course, as you understand that today was a PSAT. So this is my virtual lesson for you. And we are going to start our day 4 lessons on activity 1.2.5, work, energy, and power. So let's get to it, okay? Okay, here's my screen. As you scroll down, you're going to see October 12th, no classes, PSAT, Wednesday. And this is today's lesson right here, okay? These are 4 links, 4 or 5 links of today's lesson. And so this link right here is a page introducing what we're going to do, okay? We're going to partake in activity 1.2.5, work, energy, and power, and efficiency simulation activity, okay? In a later time, if we have time, I would like to do the physical because it's fun. It takes some building, you'll do some breadboarding, and it's a fun activity. But for now, we have to get out of this lesson what we need to in preparation for our midterm. So this second page right here will have your PowerPoint presentation slide deck where you can take your notes. I would like for you to take your notes in your engineering notebooks. The more notes you take, for me, it helps me to take notes because it helps me to retain that information better. So I would like for you to take notes, but the notes is for your review only, so it can help you. So I hope you take these notes in your engineering notebook and study them, okay? Study them every day. And if you take a look at day 1.2, day 4, item 2, this is your activity that you're going to complete and submit on Saturday, on or before Saturday, October 15th, okay? So let me go ahead and click on day 4. And again, this activity, this page was written as if you were physically in the classroom. So if you were physically in the classroom, we will partake in the activity 1.2.5, mechanical systems efficiency, VEX V5. So we will be buildings, but since we're doing the sim, we will not be doing, since we are virtual, we will not be doing the VEX 5, we will be doing the simulation, okay? So everybody go ahead and click next if you're on Canvas. Okay, so right here, let's go ahead and talk briefly about work, energy, and power. And I'm gonna give you some time to download that slide deck onto your devices so you can do the notes and step through this with me, okay? If you can just give me a few moments here. Okay. Okay, so here's our slide deck, work, energy, and power. The first slide, it talks about work, okay? And work is the energy transfer when a force is applied, a parallel force is applied to an object moving through a certain distance, okay? This equation looks a lot like moments. Do not get moments confused or mixed up with work, okay? A moment is a force that is multiplied by the perpendicular distance of a pivot, okay? Work is the parallel force times a particular distance, okay? So, so that is work. So work is done by a perpendicular force. The component of the force is parallel to the distance that the object moves. Take a look at the second bullet. The second bullet, it states that the SI unit, or the unit of the metric unit of work or energy, is the joule, okay? and the joule equals 1 Newton meter. Okay, and we'll talk about that, and I'll reference our engineering formula sheet so you can have an idea of the conversions. Okay, so let's move on to the next slide. Okay, so we have a work example. Okay, a student lifts a 50-pound ball 4 feet in 5 seconds. How many joules of work did the student complete? Okay, again, our formula for work is force times distance. Okay, so we have our force, which is 50 pounds, times our distance of 4 feet. And if you multiply those together, we have 200 foot-pounds. Okay, but it's 200 foot-pounds. The amount of work we're looking for is the unit foot-pounds, the unit we are looking for. This is the amount of work, but we need to convert this in our metric systems unit of joules. Okay, so let's talk about that. And let's talk about the conversions. Okay, so convert SI units and then calculate your work. Okay, so that's the rule of thumb. If you see a force in pounds, if you see distance in feet, we want to convert pounds into a force in newtons, and we want to convert feet, our distance in feet, in meters. Okay, those are the metric units. So let's get to it. So going back to our lesson in conversions, we have our giving unit, which is 50 pounds. We have our desired unit, which is newtons, over our giving unit in pounds, and that is our conversion factor. So we have 50 pounds converted to newtons, and you see the conversion factor, 1 Newton equals 0.225 pounds, and you divide that and you'll get 222.5 newtons. Okay, and we have to convert our feet into meters. So you'll see our giving unit, which is 4 feet, and our conversion factor. So we have 3.28 feet to 1 given meter. Okay, and we convert that, and it is 1.22 meters. And then then we can substitute and solve. So work equal force times distance. So our force is 222.5 newtons multiplied by 1.22 meters, and that is equal to 271 joules. Okay, so conversions, you'll see a lot of conversions in not only this unit. When we get to thermodynamics, you're going to see a lot of conversions. So let's get plenty of practice in converting by hand. At this time, I want to pause here. And I want to segue to our formula sheet. So let's go to our formula sheet. Okay, here it is. So let me share this with you. Okay, so we have our formula sheet, and you can use this sheet in our on our quick checks as well as our exams. And let's take a look at our conversion. So if we take a look at force, all right, so 1 Newton equals 0.225 pounds. When we were in our simple machines lesson, we had to convert our mass into newtons, right? So our mass, so force equals mass times acceleration. But right here, since pounds is a component of force, so 1 Newton equals 0.225 pounds. And then let's look at our length. All right, so we have 1 meter equals 3.28 feet, and that's just our conversions you could reference when you are taking one of our quick checks as well as our exam. Okay, so let's get back to our presentation. Okay, so we did all that. So we have 271 joules. Okay, joules of work. All right, so Let's talk about energy. Energy is the ability to do work. Okay, so light, heat, mechanical, chemical, and electrical are all forms of energy that can be used to exert a force for a distance. Okay, if you really like Six Flags, take a look at the roller coaster. Okay, so we use, again, light, heat, mechanical, chemical, and electrical forms of energy to exert a force through a distance. Okay, and then we have, forms of energy. So forms of energy. So we have several examples of forms of energy. We have gravitational potential energy that lifts an object away from the Earth's surface, that gives an object's gravitational potential energy. We have elastic energy, and that's stretching of a rubber band that gives, electromagnetic potential energy. Okay. We have electrical energy, applying voltage to a conductor that gives the conductor an electromagnetic energy. Okay. Then we have chemical energy, as well as thermal or heat energy. We're going to be talking a lot about that in our next unit when we cover thermodynamics. We have, kinetic energy, which is, a form of energy. So examples of kinetic energy, basically kinetic energy is energy of motion, the movement of a whole object, right? That is kinetic energy. We have electrical energy, which, again, is the movement of electrons in a conductor. We have thermal or heat energy, which is the movement of molecules and electrons, okay? And that is an example of the forms of kinetic energy. Okay, so we use energy, transformation. Take a look at these examples of how we use energy to transform to another type of energy. So energy transformation involves the conversion of one form of energy into another form. Okay, so let's look at some examples. Take a look at the people eating, right? We're eating some food, right? And we use the food, we consume it, so it can be converted into motion, such as sports or taking a test. Okay, very, very important, especially to eat healthy. Eat a balanced meal before an athletic contest or an exam, okay? So you can be at your best. We have chemical energy. That's, we talked about that. So we have radiant to chemical, okay? We use the sunlight is consumed by plants and is converted into energy for growth, okay? So we have radiant energy that is converted into chemical energy. Then the last example, we have electrical energy that is converted into thermal energy. So energy transferred to an oven that is converted into thermal energy so we can heat our food up, right? So those are, examples, those are examples of, energy transformation. So let's talk about, renewable energy sources, okay? So there's two types of energy sources. We have renewable energy sources and we have non-renewable sources of energy. A renewable energy source is a form of energy that is constantly and rapidly replenished by natural process, okay? And these examples include biomass, okay? So we use the use of living or once living organisms as fuel, just like this, the stalk of corn right here. We use hydropower, right? That energy produced from the movement of water, okay? That's how we produce a lot of our energy, okay? And we're going to talk more about that as we move backwards to energy sources. We talk big about, hydropower, okay? And we have geothermal, and that's the use of heat from within the earth or form the atmosphere near oceans to warm houses and other buildings. So we have geothermal, then we have wind and solar, okay? So these are examples of energy sources. Then we have non-renewable energy sources. So non-renewable energy source is one that is obtained from the earth as a liquid, gas, or solid that cannot be replenished in a rapid manner, okay? So if you use this up, it's gonna take, it's gonna take, hundreds of years for the earth to replenish. Okay, so that's why we call it non-renewable. Okay, these examples are petroleum, natural gas, coal, propane, uranium. Okay, so this slide right here is kind of segueing us to our next unit of thermodynamics. Conservation of energy. The first law of thermodynamics, first and second law, is that energy cannot be created, nor it can be destroyed, but it can change from one form to another, okay? Energy is quote unquote lost to heat, okay? When energy input, when an input energy is changed to an output energy, some of the output is usually heat energy. Let's talk about that. So again, the first and second laws of thermodynamics, energy cannot be created or destroyed, but it can change from one form to another. But why is lost in quotes, right? I mean, is energy really lost, right? So the lost is in quotations because unless there is a lower temperature, so I mean, like energy is never lost, okay? Unless it's, there is a lower temperature where heat energy can flow, it cannot be converted back into that, into another form. So that's why we say it's lost. Again, energy is not necessarily lost. They have it in quotations because it cannot be transformed back into another form. Even if there is a colder reservoir for heat to flow, in the second law of thermodynamics, it puts an upper limit on how much of the heat energy can be transferred back into another form, okay? So we're going to talk a lot about that in our next unit in thermodynamics, okay? Conservation also has a second meaning, and that second meaning is basically trying to make do with less. We do this all the time. For an example, we conserve energy by setting our thermostat to a cooler temperature for heating our homes in the winter, and in warmer temperatures for air conditioning in the summer. Okay, so this is a really good segue to our next unit. So again, energy conversion. All right, so take a look at these examples. We have fossil fuels, which is a chemical energy that is converted to heat energy that is converted to mechanical, so we can use it as electrical energy, okay? We have solar cells, all right? That is sunlight that is converted into electrical energy, which we use all the time. And then we have wind turbines, which is kinetic energy that is transferred into mechanical energy. And that mechanical energy turns a turbine, which is converted into an electrical energy. We have hydroelectric energy, which is a gravitational potential energy that is converted into mechanical, so we can all use it as electrical energy. And we also have nuclear energy, which is converted into heat, which is converted into mechanical, which is converted into electrical. Okay, so this is, how energy is converted into electrical energy so it can be usable and effective for us. Okay, let's talk about efficiency. Okay, so just like simple machines measures efficiency, we also do that in work, energy, and power. Efficiency is the percentage of input energy that is formed into output energy in the desired form. Okay, efficiency is usually written as a percentage. Okay, so let's talk more about that. And this slide basically talks about the concerns of current energy, such as the consumption of energy, the pollution, the depletion of energy, the dependency, and the cost. Right. Right now we're going through a transformation of reducing the amount of oil that we are using. And you see a lot more Teslas and hybrids, traveling around the highways. There's some issues with the extraction of oil by fracking. I saw a report in Oklahoma, and at all places, that they were having these earthquakes, and they were wondering why are they having these earthquakes, and the issue was due to fracking. They're drilling and they stopped fracking and the earthquake stopped. So there's a lot of concerns when it comes to energy and how we produce the energy, and how much it costs. So that's something to think about. Okay. And lastly, I want you to ponder on this question right here. What roles do engineers have in energy? Okay, there's a lot of different jobs concerning, engineers and energy, and how we can be more efficient and cost efficient with energy. Okay, power. Okay, power is the rate at which energy is expanded or work is performed in a given time. Okay, so take a look at the equations. Power equal energy over time in seconds, or power equals work over time in seconds. Okay, or watts, I'm sorry. So check this out. Both work and watts are abbreviated as W. Since the watt is a unit, it will only appear next to a number, whereas work is a variable and only appears with the number being multiplied by some other quantity. Okay, so the metric unit for power is the watt, and the symbol of watt is W. So 1 watt equals 1 joule over seconds. All right, so that's our equation for watts. This goes over types of power. We have electrical power, mechanical power, and fluid power. Electrical power uses electrical energy to do work. Mechanical power uses mechanical energy to do work. Gears. Think about our simple machines, gears, pulleys, etc. And mechanical energy is used, by torque and rotations, linear and rotary energy. Okay, fluid power uses energy transferred by liquids, whether it's hydraulic or pneumatic types of gases. Okay, all right, so here's our last example, and we're going to talk more about our assignment. But before we go there, let's look at our formula sheet. Let us look at our formula sheet really quick. All right, so give me a second. Where are we? Okay, so where's our formula sheet? Right here. And okay, we can see our formula sheet. I just want to point you and always refer you to our formula sheet, okay? If you're looking at defined units, you can see right here, 1 watt equals 1 joule divided by seconds, okay? So I just wanted to bring that to your attention. So let's talk more about, whoops, I'm sorry about that. Let's go back to our slideshow. Okay, so let's get into our power example. A student lifts a 50-pound ball 4 feet in 5 seconds. How many watts of power did the student use to lift the ball? Okay, so referring back to our previous slide, work, you know, we calculated equals 271 joules. Okay, now here's our equation for power. Power equals work, or watts, over time in seconds. So our work, 271 joules over 5 seconds equals 54.3 joules per second equals 54.3 watts, okay? So that's our example for work, energy, and power. So I want you to study that, do the notes, learn these equations. The equations are on your formula sheets. So you don't have to memorize them, but you know, study them as much as possible so you don't have to rely on your formula sheets. So let's talk about your homework assignment that's due Saturday, okay? So if you go to Canvas, okay, let me share my screen. Okay, if you go to Canvas and click on next, and we're at day 4, okay, and this is on your home screen as well. Actually, let me just go home. Let me just go home, and I'm going to our specific day, and I'm going to go to day 4, item 2. In item 2, this is your assignment in the PLTW lesson. Activity 1.2.5, mechanical systems efficiency simulation, and that's due Saturday at 11:59 p.m. All right. So when I click on that, it's going to take us, whoops. I think I need to redo that link. Let me just go back. Give me a second here. Let me click right here. Okay, I'll redo that. But if you click on this link right here, this will take us to the Project Lead the Way, activity 1.2.5, mechanical system efficiency sim. Okay, so you're going to read through this literature. Read through this literature, and your percent efficiency equals your power out over power in times 100%. Okay. And it goes over, it talks about electromagnetic introduction. Read all that. Then this right here, your resources give you, this is basically the slide that we just went over. And this right here is our winch construction guide. If we were doing the actual physical activity, we would use this. Again, at a later time, I would love to do this with you. It's a lot of fun. So we will do this at a later time. So here's your procedure. In this activity, you will investigate the energy conversion system designed to change electrical energy into mechanical energy. You will determine the efficiency.
Pardon the interruption for those that are still testing and doing extended testing. Please pause for just a second for these quick announcements. At the magical bell, we need everybody to go to their.
My apologies for the announcements. Let me share my screen again. Where do we leave off? Okay, so you're going to read through this activity. You're going to visually analyze, the captions, okay? Observe the display on the power source as it is set up to power the winch. Read through this, okay? Read through this activity. Watch the videos, okay? Watch the videos, okay? And observe the object and the weight. And then you're going to jot all of this down in your engineering notebooks, okay? So it took the weight and it gives you the mass in grams. Then you're going to provide object 1, the force in newtons, okay? Take a look at that again. So here's object 1, 107.01 grams. Object 2 is 107.77 grams.
Ryan Webb, please come to the office. Ryan Webb, please come to the main office.
Okay, you're going to convert our grams to our force in newtons, okay? You're going to convert that. And just follow this activity, all right? Just follow the activity. Make sure you get the length, you convert it to meters, watch the video, fill in these sections, okay? And when you're completing this activity, put your investigative hat on, okay? I want you to think about the concept as you are going through this activity. It's a fun activity, and once you do the simulation, I think it'll be real cool for us to do the actual physical. At the end of this activity, I want you to answer the conclusion questions in complete sentences. I want you to put some thought into this. And if you need some resources, you can also go to, you can go to YouTube, okay? You can go to Google. And I want you to think about the concepts that we are investigating, okay? So that's it. Once you are finished with this activity, if you go home, you can see right here, you can click on this link and you'll be able to submit your activity right here. To access the simulation, you're going to click on day 4. I'm sorry, not day 4. Yeah, day 4, item 2. And when you click on item 2, here's the link. After this video, I believe I'm going to put that link to access the PLTW activity right under here. And the last bullet will be the activity in which you need to turn in. Okay. All right. So this is due Friday. Tomorrow, we're going to segue into thermodynamics. So you have a few days on this. Have fun with it. Learn as much as you can. You all are superstars. I'm very proud of everyone. And if you have any questions, feel free to reach out to me. Okay. Have a great day. God bless. Peace.